Toxicity of inorganic toxins is a very old problem, very well studied. The identification of inorganic poisonous compounds is relatively easy because there are fewer number of them. Determination of the elements is unambiguous. We always can say which element it was. Determination of molecular toxins is usually relatively easy because these molecules are very small. One of the most dangerous inorganic toxin is carbon monoxide. It has very high affinity of hemoglobin to carbon monoxide. That gives the reason of the problem. If you have only 0.1% of carbon monoxide in air, because of this high affinity, you'll have 50% blood. So most of your hemoglobin will be substituted by carboxyhemoglobin. Therefore, it will not be available for oxygen transport, and the person will die of suffocation. So at 5% of carbon monoxide in hemoglobin, you'll have no symptoms. 5 to 10, you have impaired driving skills. 10 to 20 will give you headache. 20 to 30, severe headache and dimness of vision. 30 to 40, confusion. With around 50, it will be coma and convulsions. And 80% will give you quick death. With 90%, it's almost immediate death. Keep in mind that heavy smoker already has around 12% of carbon monoxide in blood, so impaired driving skills is visible. Several thousand fatalities are due to carbon monoxide poisoning every year, around 500 a year in the United States. Japan has from 2,000 to 5,000 in a year. Carbon monoxide can be chemically easily detected at very small concentration because of reaction with palladium ions. Palladium ions are practically colorless. Carbon monoxide reacts with them to give metal palladium, which is black, and carbon dioxide. Black color of the test strip shows that there is exposure of carbon monoxide in the room. Determination in blood is usually spectrophometrical because of different spectrum of carbon monoxide hemoglobin. Two peaks at 560 nanometers and 530 nanometers are compared. You need to know that oximeter, usual oximeter that measures oxygen in your bloodstream and is very common, simple tool, cannot detect carbon monoxide poisoning because it confuses it with oxygenated hemoglobin and gives false high oxygenated hemoglobin numbers. Very common gas chromatography method is to replace carbon monoxide with hexacyanoferrate and run gas chromatography of CO with methane as an internal standard using TCD detector. A flame ionization detector has no sensitivity to carbon monoxide. Quick treatment for carbon monoxide poisoning for living person, giving oxygen, maybe even at 3 atmosphere pressure. In that case, oxygen replaces hemoglobin complex and poisoning can be reversed, possibly. Other common non-metal molecular poisons are nitride and actually other nitrogen oxide that gives nitride. Toxic only at high concentrations, especially for children. It's food additive. There are very, very few cases. Well-known poison is cyanide. Hydrogen cyanide is 100 times more poisonous than potassium cyanide. Actually, potassium cyanide, you need lots of it to poison the person. With carbon monoxide, hydrogen cyanide contributes to toxicity of smokes during fire. When you burn certain polymers, hydrogen cyanide can be produced. Analysis, again using headspace. Treatment with sulfuric acid releases HCN that can be collected, separated, and analyzed. There are also quick color tests, hydrogen cyanide ion. Quick antidote for cyanide is sodium thiosulfate. You perhaps are familiar with that, which makes thiocyanate out of cyanide. Several other inorganic toxins have primitive, simple tests. Mercury and a couple of other toxins gives so-called range test. Shiny copper surface treated with hydrogen chloride to remove oxide from it gives black precipitate when it becomes in touch with arsenic, antimony, and bismuth. And it becomes shiny metallic with mercury. Silver will give the same reaction, but you'll never see silver, say, in blood or in urine. Fantastically simple probe, actually known for 1,000 years. Marsh probe, arsenic compound in hydrochloric acid in presence of zinc gives arsenic hydride, which is gas. Arsenic hydride, upon heat, releases elemental arsenic, which looks like a metal mirror on the surface of the tube. Alternatively, arsenic hydride can react with mercury bromide to give brightly red-orange arsenic mercury bromide, so-called Gutzeit probe. These are very simple tests for arsenic and arsenic poisoning. However, the best way to treat poisoning of elements, metals, is atomic spectroscopy. So, atomic emission spectroscopy is important for lithium. Lithium can be a poison at high concentration with overdose of lithium-containing psychotropic drugs. Also, beryllium and barium are visible in atomic spectra. For arsenic and mercury, the atomic spectroscopy and mass spectroscopy method, one of which is reaction with sodium borhydride and the resulting arsenic hydride, antimony hydride, and elemental mercury can be easily detected by GCMS atomic absorption. For small amount of poisonous compound, graphite furnace atomic absorption is perhaps the best approach because you do not need to prepare the sample. You put the sample, liquid or even solid, at amount of several microliters in a graphite tube inside the spectrometer, and then run atomic absorption processes. First you dry the sample, then for several seconds you run decomposition of organic compounds at around 400 degrees Celsius. Then very quickly, in 1-2 seconds, you run atomization all the way to 2000 degrees Celsius, after which you run the last step of cleaning at around 25 degrees Celsius, and then cool down the system, and it's ready for next test. The whole cycle takes less than 1 minute, can be easily repeated for the next sample. We have special lamps for most of toxic compounds, and for toxic compounds of interest, usually you run electrodeless discharge lamps for lead, arsenic, thallium, selenium, mercury, cadmium. All these can be toxic elements. For mercury, people often use dedicated instruments where the sample is placed in a sample boat. It's drying and decomposing at temperatures from 120 to 750, running through catalyst to decompose the organic compounds of mercury, and then coming to amalgamator. Mercury easily absorbs on surface of gold. This is very selective process and can be used for future analysis. So you collect your gases coming from your sample on this amalgamator, and after collection is done, increase temperature of amalgamator, and the mercury from the sample is coming into spectrophotometer. That runs on one single line of mercury. We are not going to detect any other elements. Alternatively, you can run sample processing in a very simple fashion. First, digestion your organic mercury and inorganic mercury with nitric acid. Then oxidize your organic mercury compound into Ag2 plus with permanganate. So they react with permanganate, organic gives CO2, and mercury becomes inorganic mercury. Extra permanganate is removed by hydroxylamine. And then put your sample into the analyzer, which will reduce remaining traces of permanganate and reduce mercury ions to mercury atoms, which are pushed by nitrogen into the atomic absorption cuvette and measured by atomic absorption spectroscopy. These all methods are of fantastic selectivity. No other elements can react having mercury lines, and of a very high sensitivity. We are talking about parts per trillion.